It's roughly minus 50 degrees at the end of the world. In front of us lies a stretch of ocean that honestly doesn't even look like an ocean. It looks like a living field of ice, groaning, shifting, never still. And on the other side of this frozen abyss stands the most audacious project humanity has ever imagined: a bridge linking North America to Asia. This isn't about crossing a calm river or a quiet bay. This is the Bering Strait, where the ground cracks, splits apart, and crushes anything that tries to stay fixed. So, how the hell do you build a bridge here? You don't start with towers. You don't start with concrete. You start with a simple mission: survive long enough to build anything at all. Because in this place, the problem isn't construction. The problem is making logistics work. Before a single foundation is placed, teams must create something the Arctic never offers willingly: a stable corridor. First come the icebreakers, massive ships carving paths through frozen seas, opening routes so the logistics fleet can even get close. But the ice here isn't just thick. It's under constant pressure. It drifts, collides, compresses. And the moment you open a passage, the ocean tries to close it again, as if healing a wound. There are no reliable ports, no normal supply chains, no convenient assembly yards. So the first real act of construction isn't part of the bridge at all. It's the base camp's entire modular cities flown in and assembled under brutal conditions, heated, sealed, reinforced. Without them, nothing happens. And if the heating fails, the project doesn't pause. It dies. These camps become the bridge's lifeline, housing power, medical facilities, maintenance shops, welding stations, everything that keeps thousands of workers alive on a constantly moving frozen sea. But even with the camps ready building, anything above would be pointless if you don't know what you're building on. The seabed of the Bering Strait is treacherous sediment over rock-weak layers that shift under pressure pockets that react differently as temperature and depth change. Before drawing a single pillar, engineers hunt for something rare in the Arctic: certainty. Marine scanning systems map the geology beneath the silt. Drilling platforms probe deep, searching for anchor points capable of holding a structure for generations. Every decision here is unforgiving. Steel doesn't just get cold, it becomes brittle. A bad weld can shatter like glass. That's why the project doesn't just bring materials, it brings manufacturing capability. Floating barges and mobile plants fabricate structural components and specialized concrete near the site, because transporting everything pre-made through this environment is too risky. And ordinary metals won't do. The bridge demands cryogenic steel engineered to withstand extreme cold without cracking when temperatures plunge. Then comes a challenge that sounds like a joke, but isn't. To build a bridge, you need heavy trucks. And to drive heavy trucks over sea ice, you have to build the ice. Natural ice may be thick, but not thick enough to handle daily convoys carrying hundreds of tons. So teams do something straight out of a movie. They artificially thicken the ice, flooding the surface and letting it freeze layer by layer until it becomes a reinforced platform capable of supporting heavy transport without turning into a catastrophe. At the same time, there's a critical piece in the middle of the strait, a rocky island near the center. It becomes the heart of the plain because it offers what ice never will: something that doesn't move. The island is cut-leveled, brutally reshaped into an assembly hub, transforming raw Arctic stone into a launch point for megalifts and precision placement. Then arrives the machine that unlocks the next phase, a Titan crane built for absurd loads designed to lift thousands of tons while fighting brutal winds and freezing spray. Just assembling and anchoring this monster takes days. And every lift becomes a gamble because here, the wind is in background noise. It's a force capable of turning a suspended steel segment into a swinging hammer. Once that crane is finally locked in place, the project crosses a line. Now something permanent can begin. And that leads to the moment everything has been preparing for sinking the first foundation. This isn't something you simply drop and pour. It descends like a lunar module. A massive steel template is lowered into dark, near-freezing water, guided by sonar and underwater robots, because visibility is minimal and tolerances are brutal. It has to land perfectly, dozens of meters down in darkness, while the ice above continues to move. When it finally touches bottom and aligns precisely, only then does the real work begin, driving deep piles into solid rock beneath the seabed. No shallow support, no good enough. These piles must withstand moving ice storms, violent tides, and decades of fatigue. Driving them is a violent process. The impacts travel through water and ice as if the entire ocean feels the blow. And still, everything must be exact, because here, a small mistake becomes a massive problem. Then comes the concrete, but not just any concrete. These are specialized mixes designed to cure underwater in near-freezing conditions. Yet concrete has its own betrayal. As it cures, it generates heat. If temperature changes unevenly, it can crack internally unseen until it's too late. So engineers control the curing process like doctors in an ICU, monitoring temperature, adjusting insulation, ensuring the structure hardens without thermal shock, while the ocean tries to steal heat faster from one side than the other. When the first pier finally breaks the surface, it's not a moment of celebration, because in the Bering Strait, a newborn pier already has an enemy waiting: winter pack ice. Here, ice doesn't gently press. It crushes. It grinds. It sands everything down over time. That's why the piers aren't smooth and round. They're shaped like blades forms that split and deflect ice sheets, forcing pressure upward and around the structure instead of straight into it. On top of that comes an outer layer of armor protection against constant abrasion, because the surface will be attacked non-stop. One by one, these steps emerge. Each new pier is another fixed anchor in an environment that wants to move. Until finally, there's a chain of stable supports crossing the strait. And then the project changes, phase leaving survival mode and entering ascent mode. Now it's time to raise the towers, the structures everyone will recognize from afar, and say, this is a real bridge. But here, towers aren't built the normal way. The cold doesn't just slow crews, it threatens the material itself. Concrete can freeze in layers, formwork can lock up, curing can fail. So the towers rise using slip-form construction, a climbing mold system that moves slowly and continuously, an hour after hour, day and night, leaving hardened concrete behind like a growing spine. As the tower rises, the climate becomes monstrous. Up there above the ice, the wind cuts with an almost absurd force. Wind chills can plunge to minus 70 degrees Celsius. In those conditions, no one works normally. Crews operate in short bursts to avoid frostbite. Even simple tasks become battles: tightening bolts, guiding rebar, aligning braces, everything done with numb hands and a ticking clock. As the tower gains height, the elements that keep it alive in the wind come into play: bracing and cross members. Because the wind here doesn't just push, it twists structures like a wrench. The design must accept a frightening truth: the bridge has to flex. It has to move. And that's correct. Make it too rigid and it breaks. So the structure is engineered to yield without failing, absorbing storms instead of confronting them like a wall. At the top, massive components are installed: saddles, huge metal supports that will carry the bridge's backbone, the suspension cables. And then comes the phase that turns the project into an industrial-scale circus act, connecting cables across the span. You don't start by pulling a massive cable out of nowhere. You begin with a pilot line, a thin, almost harmless thread. A drone or specialized system carries that initial line across, and that line becomes the guide for everything that follows. Because then begins the weaving of the main cable. This is the spinning process, thousands of back and forth passes, laying individual wires one by one, each trip adding strength and mass until the cable exists, not because it was placed, but because it was woven in midair. Months later, that bundle of thousands of wires is compacted and bound into a single cable. It can't behave like separate strands. It must act like an artery, one solid piece carrying immense weight. Then come the hangers, the vertical elements connecting the main cable to the deck structure. This is when the bridge truly starts to look like a bridge, as the web that will support the roadway takes shape. But the road itself, is far too heavy and risky to build up there amid this chaos. So it's fabricated elsewhere, in massive sections, where precision and climate can be controlled, then transported like a colossal puzzle. Each segment weighs thousands of tons. Lifting them is slow, surgical, and terrifying. Because the wind can turn a segment into a pendulum. One wrong swing and it becomes a weapon. So everything is controlled to the millimeter. The crews wait high above to receive the incoming segment, align it, seat it, and lock it into the hangars. There's no almost. Alignment must be exact before final welding and permanent fixation. To reduce human error, automated welding and inspection systems ensure uniform joints. Because a flaw here isn't just ugly, it's something the Arctic will punish for decades. Segment by segment, the deck advances from both sides until the most symbolic moment arrives, the final piece. The closure segment, the one that seals the gap. And when it drops into place, something that once sounded like legend becomes real continents physically connected. But even then, it isn't over. A fully exposed roadway in the Bering Strait would be a nightmare to drive and far too dangerous. In near-polar hurricane winds, stability isn't a luxury, it's a requirement. So this bridge would do something highly unusual. At this scale, it would close itself in. Metal rib structures rise above the deck, forming an aerodynamic shell. Layered panels seal everything, designed to withstand extreme cold impacts and prevent ice buildup. Outside is chaos. Inside becomes a controlled environment. With the envelope-complete systems, move-in durable pavement signage, emergency shoulders, thousands of LEDs, turning polar night into day ventilation to remove exhaust sensors, fire detection, and suppression, because an accident inside a sealed tube cannot become a disaster. And there's more ambition still reserved: infrastructure corridors for future rail, because this isn't just about cars. It's about cargo, freight, creating a continuous land route between continents capable of reshaping global trade routes. Then comes the phase that separates an impressive project from a historic one inspection and proof of life. A bridge of this scale in this place can't be approved by intuition. It has to be numbers, data scans. So begins a battery of checks, every component measured, every weld inspected, using scans, ultrasound sensors, integrity tests, deformation readings, alignment. verification. And then comes the test everyone waits for: extreme load testing. Massive convoys roll in, carrying controlled weights designed to simulate worst-case scenarios. They cross the bridge slowly and methodically, recording every vibration, every microflex, every system response. The idea is simple: if it survives the worst, it survives everything else. Once the test passed, the project enters dismantling mode for what was temporary. Base camps are removed. Reusable elements are taken away. Waste is cleared. Work zones are cleaned. Heavy equipment is towed out, and the scene changes. The ice continues moving as it always has. But now, there's something that doesn't depend on it: a structure of steel concrete and protective systems spanning a hostile sea. And then comes the moment that turns engineering into history: the first crossing. You start on the Alaskan side. The entrance is smooth, strangely quiet. Outside, the world is screaming wind-grinding, ice-cracking, colliding plates. But inside the bridge's shell, you feel almost nothing. You drive, and the surreal sets in. Below, the ice cracks and slides as always. The ocean tries to be an ocean again, and you pass above it on a route that for millennia would have been impossible without a ship or an airplane. Halfway across, you pass the central island, now the strongest anchor point in the entire system. And it hits you at this point: you're closer to Russia than to much of the United States. You keep going. And suddenly, something that for ages would have sounded like myth becomes reality. You cross from the U.S. to Russia, without a plane, without a ship, just a road. Two continents separated by distant ice, and centuries of history connected by a structure raised in one of the most brutal construction environments on Earth. And the wildest part: this didn't happen because the Arctic became kind. It happened because engineering learned how to fight it.